Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from beta gamma functions, right? In our earlier videos we have already solved a number of problems related to a beta gamma function, right? So in this lecture we'll solve this important integral in which we'll make use of the definition of gamma function, right? So let us start and let us see how we can easily solve this type of integral by the method of substitution, right? So let us first call this integral as I, right? Now see, in the denominator we have 2x plus 3 raised to 6, right? And the overall integrand is x cube divided by 2x plus 3 raised to 6, right? So what we will do, we'll take 2x is equal to uh, 3t, right? So here we are introducing this variable t, right? So why we are writing 2x is equal to 3t? Because see, this term 2x plus 3, when we take 2x is equal to 3t and substituting 2x is equal to 3t in this expression, we have 3t plus 3, right? And we can easily see that we can take 3 common from this term, that is t plus 1, right? So that's why we are taking this substitution, 2x is equal to 3t, right? So when 2x is equal to 3t, then we have x is equal to 3t over 2, right? So let us differentiate both sides with respect to t. So dx over dt is equal to 3 by 2 times 1, because the derivative of t with respect to t is 1. So we have 3 by 2, right? So now dx can be written as 3 by 2 times dt, right? So now we have dx is equal to 3 by 2 times dt, and let us change the limits accordingly. So here x varies from 0 to infinity, right? So when x is equal to 0, we can find out the value of t by substituting x is equal to 0 in this relation. So we have 3t is equal to 2 times 0, that is 0. So t is equal to 0 divided by 3, that is 0, right? And when we have x is equal to here infinity, then we have 3t is equal to 2 times infinity, that is simply infinity, and t is equal to infinite, right? So now we can rewrite this integral I in terms of t, right? So the limits remains the same. So t varies from 0 to infinity. For x cube, we have 3t over 2 raised to 3, and for dx we can now write 3 by 2 dt, right? Okay, and in the denominator we have 2x, so 2x can be replaced by 3t, and here we have 3, and this is raised to 6, right? So now what we have to do, we have to take the constant terms out of the integral. So here we have 3 cube, 3 cube is 27, 2 cube is 8, right? And here we have 3 by 2, and now we have 0 to infinity. We are simply left with t cube, and here we have dt. And see, here if we take 3 common, then we have 3 raised to 6 and t plus 1 raised to 6, right? Okay, so now we can take this 3 raised to 6 from this integral. So we have here 27 3s are 81, and 8 2s are 16, and then we have 3 raised to 6 outside the integral. We have 0 to infinity. We have t cube dt divided by t plus 1 raised to 6, which can be written as 1 plus t, because t plus 1 and 1 plus t are same. So here we have 6, right? So now let us simplify these terms which are outside the integral. So here we have 81 and here we have 16 and 3 raised to 6 is 729, right? And now see this integral, right? So here we have 0 to infinity. Now see, t cube can be written as t raised to 4 minus 1, right? So 4 minus 1 is 3. So why we are writing? Because we are now converting this integral into beta function, right? So t cube can be written as 4 minus 1 and 1 plus t raised to 6 can be written as 4 plus 2, right? Because 6 we can split 6 as 4 plus 2. So now viewers, so we can simplify this expression. So here we have 81 9s are 729 and 16 times 9 is 144, right? And here we have 0 to infinity and t raised to 4 minus 1, we have 1 plus t raised to 4 plus 2 dt, right? So now our integral it looks like this, right? Okay, now here we have to use the definition of beta function, right? So now see the beta integral, we have already discussed a lot about this function in our earlier videos. So the beta function, that is beta mn, can also be defined by this integral, that is 0 to infinity x raised to m minus 1 and 1 plus x raised to m plus n, right? So this is another definition of beta integral, right? So now see our this integral is exactly same as this one, except the variable. Here we have the variable t, here we have the variable x, right? So we can ignore it because this is a dummy variable. So here x raised to m minus 1, 1 plus x raised to m plus n. So if we compare this integrand with this one, then we can see that m is equal to 4 and n is equal to 2, right? Because this is m, this is m, and this is our n, right? So now our integral I can be written as 1 over 144, and here we can replace this integral by beta of mn. Mn is 4 comma 2, right? So now viewers, we have to find out the value of beta 4 comma 2, right? So we know that beta mn is defined in terms of gamma function, that is gamma of m, gamma of n divided by gamma of m plus n, right? So here beta 4 comma 2 is equal to gamma of 4, gamma of 2, gamma of m plus n. So 4 plus 2 is 6, right? So here I will make use of one important result from gamma function. So gamma of n plus 1 is equal to n factorial, right? Where n is greater than 0. So here we have gamma of 4. So gamma of 4 can be written as 3 factorial, gamma of 2 can be written as 1 factorial, gamma of 6 can be written as 5 factorial, right? See, gamma of 4 can be written as gamma of 3 plus 1. So here n is 3. So we have 3 factorial, and likewise here we have gamma of 2 and gamma of 6, right? So 3 factorial is simply 6, 1 factorial is 1, and 5 factorial is 120, right? So this is 1 over 6 to the 12, so we have 1 over 20. So now the value of I is 1 over 144 times 1 over 20, right? So beta of 4 comma 2 is 1 over 20. So now we can multiply these two numbers and we'll get 1 over 2880, right? So here's the value of this integral is equal to 1 over 2880, right? So this is how by making use of this definition of gamma beta function, we can solve these kind of integrals. Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from integrals, right? And in this class we are going to discuss this integral, right? So here we have to evaluate this integral from 0 to 2, and our integrand is x square over square root of 2 minus x, right? So here again, we'll make use of the concept of beta gamma function, right? So let us start and let us take this integral as I, right? So viewers, what we will do here, will again make use of the method of substitution, right? And the method of substitution is a very powerful method in integration. So here, what we will do, we'll take x is equal to 2t, right? So this is the most appropriate substitution in this integration, right? So we'll take x is equal to 2t. Why we have taken x is equal to 2t? Because see, in the denominator we have the term inside the square root sign as 2 minus x, right? So when we take x is equal to 2t, then we have 2 minus 2t, right? And now we can easily take 2 common, right? So here we have 2 1 minus t. Okay, so now we'll take x is equal to 2t. So dx over dt, that is differentiating both sides with respect to t. We have the derivative of t with respect to t as 1. So we have 2, right? So now we can write dx is equal to 2 dt. Okay, so now here the limits of integration vary from 0 to 2. So we have to change the limits accordingly. So when x is equal to 0, then we can find out the value of t from this relation, because we can also write t as x over 2. So t is 0 over 2, that is simply 0. And when x is equal to 2, we have t is equal to 2 over 2, that is 1, right? So now we can rewrite this integral I in terms of t. So we have now limits of integration going from 0 to 1, and x square can be replaced by 2t square, and here dx can be replaced by 2 dt, right? And in the denominator we have square root of 2 minus x is 2t. Here we have 2t, right? So we can take the constant terms outside the integral. So here 2 square is 4, 4 2s are 8. So we have 8 here, and we have 0 to 1, and in the numerator we have t square. This is dt, and if we take 2 common, then we have square root of 2 outside the integral, and in the denominator we have square root of 1 minus t, right? Okay, so now we can simplify, or we can rewrite this integral as 8 over square root of 2, 0 to 1. We have t square, and square root of 1 minus t can be written as 1 minus t raised to half, and taking this denominator to the numerator, we have 1 minus t raised to negative half, right? And here we have simply dt. So now we have this integral, right? So now we wish to convert this integral into the beta function, or the beta integral, or which is also known as Eulerian integral of first kind. So we have 8 over square root of 2, 0 to 1. T square can be written as t raised to 3 minus 1, right? And 1 minus t raised to minus half, which can be written as half minus 1 and dt, right? So we have expressed t square as t raised to 3 minus 1 because this is going to be our m, and minus half is written like this, half minus 1, this is going to be our n, right? Because see, the beta integral or the beta function is defined as 0 to 1 x raised to m minus 1, then we have 1 minus x raised to n minus 1, here we have dx, right? So comparing this integral with this one, we have m is equal to 3 minus 1, this is m minus 1, so m is 3 and n is half, right? So here we have half. So now this integral I can be written as 8 over square root of 2, then we have beta of m comma n, m is 3 and n is half, right? So now we have to find the value of beta 3 comma half. So now in order to get the value of beta 3 comma half, we'll make use of this result. Beta mn is the relation between beta function and gamma function is gamma m gamma n divided by gamma of m plus n, right? So beta 3 comma half is equal to gamma of 3 gamma of half, and in the denominator we have gamma of m plus n, so 3 plus half is 7 over 2, right? So here we have gamma 7 over 2, right? Now see, gamma of 3 can be written as simply 2 factorial, which is 2, and here gamma half can be replaced by square root of pi, but we'll cancel it out from the denominator, right? Now see, gamma of 7 by 2 can be written as gamma of 5 by, we can write it like this, 5 by 2 plus 1, right? So this is 5 by 2, gamma of 5 by 2, right? And further we can write gamma of 5 by 2 by writing 3 by 2 gamma of 3 by 2, and then we can write 3 by 2 gamma of 3 by 2 as half times gamma of half, right? So this quantity is equal to this expression. So here we have made use of this result, that is gamma of n plus 1 is equal to n times gamma of n, right? So here 7 over 2, so we have written 7 over 2 as 5 by 2 plus 1, so our n is 5 by 2, so we have 5 by 2, that is n times gamma of n, that is gamma of 5 by 2. So successive application of this formula leads to this expression, right? And here we have written gamma of 3 as 2 factorial. 2 factorial is simply 2, and here we have made use of this result, that is gamma of n plus 1 is equal to n factorial, right? So 3 can be written as 2 plus 1 and n is 2, so we have 2 factorial, right? So now we can write 8 over square root of 2, and beta 3 comma half is now equal to gamma of 3. Gamma of 3 is 2 factorial, which is 2. Then we have gamma of half, and then we have gamma of 7 over 2, which is 5 over 2 times 3 over 2 times half, and here we have gamma of half, right? So now these two terms get cancelled, right? And always remember that gamma of half is equal to square root of pi, right? Okay, So now we can simplify this expression. This is 8 to the 16 over root 2, and we have now 2 to the 4 to the 8. We can take 8 to the numerator, and here we have 5 3s are 15, right? So now we can have here a 16 8s are 128, and this is 15 times square root of 2, right? So the value of this integral is 128 over 15 times square root of 2. So we can also express this result by rationalizing the numerator and denominator by square root of 2. That is 128 over 15 root 2 times root 2 over root 2. So here root 2 times square root of 2 is 2, and we can cancel 128 by 2, that is 64, and here we have root 2, and we are left with only 15, right? So the value of this integral may also be taken as 64 root 2 divided by 15, right? So viewers, this is how by making use of the concept of beta gamma function and their properties, we can evaluate these kind of integrals.